So let's see. So going back to the 2018 practice, Q3 2018. So this is something you guys can, of course, currently access on Canvas as well. And what do we have here? So the first question, and actually let me preface this first question by saying that this exam is cumulative, so it will cover all the concepts in the course. And so it is more heavily weighted towards more recent material towards the end of the course for sure, but definitely you can expect to see older content as well. And so that means that in terms of studying, perhaps looking through the exam 1 and exam 2 that you took earlier, that might be a smart thing to do as well. Maybe briefly looking through the older homeworks as well. The newer homeworks I would recommend looking through anyway and making sure you can solve all those problems if they were given to you in an exam setting. But, maybe briefly doing the same thing with the earlier homeworks just to refresh those concepts in your mind. And because, really any concepts in the course are fair game. And so, I just wanted to mention that. So this first question is one such question. I believe this question would have felt right at home on the first exam as well, where we have two random variables. We have x and we have y, and they have a joint PDF, f of x of y, by this equation, and we have bounds for y and x. And this question's kind of mean. It doesn't actually tell us what this constant c is. We have to figure that out through the problem. But the problem doesn't actually ask us to find c. The problem wants us to find e of x. So rather than jumping into what they do, the first thing I would, when looking at a problem like this, how do you approach it? So when you have e of x, that's the primary thing that you need to get. But in order to actually calculate e of x, so the definition for e of x with continuous variables is you integrate the PDF f of x, and because x is in the expectation, you multiply x by the PDF and you integrate it over the entire range where there is positive probability density. So in this case, x can be from 0 to 1, so 0 to 1 are our integration limits. And so that's the first thing. So you're like, okay, cool. So I just need to do this integral. Well, that's fine, except this problem doesn't actually tell you what f of x is. It tells you what f of x comma y is. So it tells you the joint probability distribution. And so what you, of course, being a well-studied student in this course, will realize is that, oh yeah, you can actually go from this to this by doing some smart integration, basically. And basically, the integration is pretty, straightforward. So to get f of just a single variable from this joint, you do f of x is equal to, you integrate the joint probability distribution over basically with respect to y, over the entire range where that y can be. However, because y actually depends on x, so y has to be between 0 and x, that means our integration bounds will be from 0 to x. So we know we could plug this in here, but there's still a problem, and that is we still don't know what this constant c is. So before we can actually do this integral to get this, so that way we can plug it in here so we can do this integral, we have to figure out what this constant c is. And so, this is kind of a obnoxious question in that sense, where you actually have to do a series of basically 3 different integrals to get the final answer, which is a little obnoxious, I will admit, but it is necessary in this case. And so, how do we find c? Well, there is sort of a universal truth that there's, I guess, a couple different ways you can go about doing this, but basically there's a universal truth that this joint probability distribution, if you integrate it over all values of x and all values of y, you have to get 1. Like, you have to get this integrated to be equal to 1, which represents 100% of the probability distribution. And so that's sort of what they're doing here. They are saying 1 is equal to, and you have these integration limits, and here we have f of x comma y, this joint thing gets put in here. And you'll notice that the first limit of integration is dy, and we go from 0 to x because y here goes from 0 to x. And then our outer limit, where we no longer have a y variable to worry about, we can go from 0 to 1 for the outer limits. And so at that point, it's sort of a matter of running the integrals. And I'm happy to run through the integrals. Yeah, does somebody want me to do this integration by hand to get to this answer? What do people feel like?
Yes, please, it'll be helpful.
Okay, it'll be helpful? Okay, well, there we go. So let's do that. Let me open up a different place to write. So here we go. So basically what we want to do, recall we have f of x comma y equal to c 1 minus x times y from 0 to y less than x less than 1. And we want to figure out what c is. So we have our integral. Well, I'll just redraw this here, 0, 1, 0x, and then c 1 minus x, y dy, and a dx on the outside. And so the first thing we'll do is we'll do this integral. So this inner integral, we integrate it with respect to y. So notice that there is no y in c and there's no y in 1 minus x. So really you can treat this whole c times 1 minus x as a constant, and this y is the only thing that needs integrating. So that ends up being c 1 minus x and then y squared over 2. And we want to evaluate it from 0 to x, so 0 to x. And of course we still have the outer integral, so we'll throw that in here. So that's 0 to 1, and the outer integral is dx. So at this point, all we've done is we've integrated the inner integral, so y becomes y squared over 2, and we keep this constant and everything. And then the next step is we plug in the limits, so x goes in here, and that becomes x squared over 2. This 0 basically just zeroes out, so it's just like we can, like if I do this, so I have this outer limit here, c 1 minus x, that's fine, and then plugging in this x into here, using these limits, we have x squared over 2 minus 0 squared over 2, and of course dx, and of course 0 squared over 2 goes goodbye, so we're just left with c times 1 minus x times x squared over 2 dx. And the next thing we can do is we can we can write this a little bit more nicely. So we have 0, 1, and we can sort of multiply this c by this 1, and then multiply that by the x squared over 2. So we have c x squared over 2. And then we can multiply the c by the minus x, so that's minus cx times the x squared over 2. So that's minus cx cubed over 2. And so and this is of course all dx. This is still one integral. And then what we can do is we can continue. We can this time do this integral. And so this becomes cx cubed over 6 minus cx to the 4th, if I'm doing this right, over 8. And this is evaluated from 0 to 1, so evaluated like that. And we can kind of more nicely rewrite this as sorry, ignore what I just said. The next thing is we want to plug in this 1 and 0, which are the values that we're evaluating it as. And so, of course, 1, when plugged into x to the 4th and x to the 3rd, is just going to equal 1. And the 0 is going to make those respective terms go away. So we end up with c over 6 minus c over 8. And sort of, one thing we can do is we can factor out the c, and we have 1/6 minus 1/8. And if you sort of do common things, this is 4 out of 24. This is 3 out of 24. We see that it's equal to c over 24, like that. And remember that we started off by doing all of this by knowing that the integral of all of this has to equal 1. So we set that equal to 1, and that tells us that c is equal to 24. And so now we've found what the value of c is, and that's pretty much that. So now that we know what the value of c is, now we can plug in, now we can actually do this next integral here, where we calculate the marginal probability density function f of x. And so which is going to be another integral, but I don't know, I might as well just go through it, I guess. So if we sort of continue this, what we want to do is we want to calculate this marginal distribution f of x. So we know that f of x is equal to the integral of f of x comma y dy. Y dy, like that. And what are the limits of integration? Well, technically the limits of integration are, basically all x values, but we really only need to worry about the values where f of x is non-zero, and that is for from 0 to x because of this. So, where this thing, is non-zero, and that's only from 0 to x when we're integrating with respect to y. So, I just have to write this. So f of x comma y is equal to c 1 minus x times y, so c 1 minus x times y. And recall that this is from 0 to x, if I'm doing this right, yep, dy. And we know that c is equal to 24, so we plug it in there. And so next we have 24, 1 minus x, y, dy. And we integrate with respect to y. So that gives us, let's see, so we keep the 24, and we keep the 1 minus x, and then the y becomes y squared over 2. And we do this from 0 to x, which once again, this 0 value sort of if you do the full math, it disappears. So this is equal to 24 times 1 minus x times x squared over 2, which can be more simply written as just 12 times, so this becomes 12 is 1, and then 12 times 1 times x squared, so that's 12x squared, and 12 minus x times x squared is minus 12x cubed. Cool. So this is our marginal distribution now. And at this point, we only have one final step left, and that's to actually calculate the expected value. So the expected value of x, recall, and really you can put anything you want into these brackets, and let me scroll over here just to give an example. So we can have expected value of, let's say, like, I don't know, x, y, z. So we can have some weird thing, and in all cases it's equal to the integral of whatever the actually, maybe this isn't a very good let me give a better example to not confuse you guys. Sorry. Eraser, where's my... Let's say we did like e of 3x, then we put that 3x into the integral, and we still have f of x like that. So that's if we had e of 3x. In our case, we just have e of x, so we just put integral of x times the probability density function f of x, which we calculated here. And you want to integrate it over everywhere that the probability function is non-zero. And in our case, of course, that is from 0 to 1. So our limits of integration are 0 to 1. So at this point, we plug in this integral. We plug in this function, this marginal distribution, into this integral, and then do the integration. So 0 to 1, x times 12x squared minus 12x cubed, like that. And continuing, continuing, we can sort of multiply these out. So this is what, 12x cubed minus 12x to the fourth still, and we still have these integration things here. And now we actually do the integral, so this becomes 12 over 4x fourth minus 12 over 5x to the fifth. And this is evaluated from 0 to 1, and that leaves us with 12 fourths, if I'm doing this math right, minus 12 fifths. And this, of course, is just equal to 3. That's equal to 3. And then this other one's equal to, like, 2.4. And so you end up with 0.6, which, if I did all my math correctly, should be what the answer is. Yep, okay, great. So, cool. Any questions on that?
Is there any shortcut for all? It just feels like this is gonna be forever just to finish one problem.
Pushing the constants out, I think, is one way you can, like the 12s and 24s, and those could be outside the integral. I think that's what we did when we...
Yeah, there's ways you can sort of simplify it. I obviously was going really slow step by step to sort of show things to you guys. But yeah, it could be a little bit faster in real life. But in terms of ways to speed it up, there's Not a great way. You really have to figure out what C is, and you really have to figure out the marginal distribution. And to do that, unfortunately, you kind of have to do integrals. Um, yeah, and this is kind of a true statement about the test. There are some questions that will take a lot longer, and there are some questions that will take a lot less time. Like there's some true and false questions where you'll have the answer like that, and you'll be able to put it down and move on. And that's just sort of the nature of the beast. Um, you know, I know you guys, I think you guys get a pretty long amount of time for the test, so I forget how much time it is, but yeah, like with anything, if good test taking strategies might involve leaving this one for the end because it just is more time intensive and trying to do the ones that take less time and then coming back to this one, as time permits. That's one thing you could do on a test.
Yeah, because we get about 3 minutes a question on an average.
Yeah, so obviously me walking through this was longer than 3 minutes, but there, as I mentioned before, there's a lot of questions that take a lot less than 3 minutes. So, yeah. While I'm here, I did also want to talk about variants of this question. So, this is one form of this question that you might get, but, the question might also be asking, okay, what is, tell us what f of x is. And that's easier than finding out e of x, but you still have to figure out what c is, and you still have to integrate this f of x of y to get this f of x. But, that's a variant. Another variant is you could be told, tell us what is f of y. That's another variant. Another variant you could be asked is, are x and y independent in this case? And, that would probably be phrased as a true or false question. But of course, for this question, the answer to are x and y independent, the answer is false because the, you can see in these funky, bounds that the value of y literally depends on the value of x, so they can't be independent. That runs counter to the idea of independence. So that's another kind of form that you might be asked. Another thing.
So what will be the fy? The f of y? This.
So to get f of y, you would integrate f of x comma y with respect to dx, and calculate that out, whatever that is.
Okay. Thank you.
Yeah. So you can see that this is very similar to this. So f of x, you integrate it with respect to y to get rid of the y's. And then to get f of y, you integrate this to get rid of the x's. So anyway, that's how you do that.
So the variants, like you mentioned, we have seen are the questions on independence with different types of expressions. So what would be the correct way to check for independence? Is it just factorizing and trying to see, or what would you suggest to test for independence?
Yeah, so in this case, there's two aspects. So you can definitely, this thing is factorizable to be the things that contain the x's and contain the y's, but the bounds of the variables themselves are dependent on each other, and therefore these variables are dependent. In order to have these be independent, you would have to both have the joint PDF factorizable, and you'd have to have the limits be independent. For example, an example of independent limits might be something like this: 0 less than y less than 1, comma, 0 less than x less than 1. And you can see that in this case, x and y don't depend on each other in the bounds at all, but here they do. Cool?
Thank you.
Yeah. One other thing I wanted to briefly mention while we were here is that there's a bunch of other sort of similar, how should I say, situations to finding the expected value of things. So, for example, or in this case, in problem one, we had a continuous distribution. So, this is continuous. But you could imagine a scenario where you have discrete random variables, and suppose that your discrete random variables, you have x and y, but x can be equal to 1 or 2, and y can be equal to 5 or 10, and basically we can draw out the we have, maybe there's a probability of 1/2 of that happening, 1/4 of this happening, 1/8 of this, and 1/8 of that. And so this is the, P, the joint, let's call it joint PMF for X and Y is this thing. So that means that, for example, the probability that you see X equals 1 and Y equals 10 together is equal to 1/4. And, so that, but you might be asked questions. You might be told, okay, given this joint PMF, tell us what E of X is, or what E of Y is, or they might even say, tell us what the variance of X is, or they might say, tell us what the covariance of X comma Y is. These are all valid questions that could be asked, and in my opinion, you should hopefully know how to do this, or if not, maybe review exam 1 on how to do that. Or review older concepts. But I just wanted to point out that, the alternative variants of how this question could show up. In this case, it showed up in the continuous case where you have a bunch of integrals, but it could also show up in the discrete case where you have to do a bunch of discrete summations in order to get things. Any questions so far? Well, stop me if you think of any questions.
Maybe just one tiny one. Is it fair game to see something about the correlation here too?
Maybe. Was it on exam 1?
I think exam 2 had some. I mean, we were given expected values already. We just had to kind of like figure out how to put them together in order to find a correlation. But in the past,
I would say it's definitely fair game, and you can definitely, you might have to potentially calculate it. Yeah. So recall that let me go back to my whiteboard thing here. So recall that our correlation, I think it's rho usually or whatever. It's equal to the covariance of x comma y. X comma y divided by the square root of the variance of x and the y. So var x and var y, like that, if I'm not mistaken. And so that's our correlation. You might be asked to calculate it. That is also fair game. You can imagine a scenario where you're given, for example, this, and there, maybe it might be a multi-part problem where first they tell you to find E of y, then they tell you to find covariance of x comma y, and then at the end they tell you to find the correlation. That would be kind of maybe a little bit mean and a little bit involved, but it could happen. You never know. So know how to do it. One thing I will mention about the correlation is that, and this is, I think, a question that many teachers, many professors, including Dr. Goldsman, sometimes like to ask, and that is, so it's the relationship between correlation and independence. So if x and y are independent, then the correlation equals 0. So that's definitely true. However, going the opposite way, so if the correlation is equal to 0, then x and y might be independent, but they might not also. Might be independent, but they also might not. And so a potential test question might be a true and false, where the true and false might show you this statement here, where if x and y are independent, then the correlation is equal to 0, and that would be true. Or they might give you the opposite thing, and they say if two variables have a correlation of 0, then they must be independent. And if they put that as a true and false question, then you would of course write false, because going the other way does not necessarily happen. Yeah. But yeah, definitely correlation is fair game. I don't think I saw correlation on this particular past exam, but I definitely think it's fair game. Does that answer your question?
Absolutely. Thank you so much.
Mm-hmm. Great. Cool. So question 2. So if x and y are IID Poisson 3 random variables, find the variance of x times y. So in this case, basically, when you see something like this, the first thing that comes to mind is you know that what the random variables are, and you know, because hopefully you wrote it down on your equation sheet, you know like the expected values and the variances and the CDFs, etc., for different distributions. So we know that, for example, for a Poisson random variable, we know that E of x is equal to lambda, and we know that also the variance of x is equal to lambda for Poisson random variables. And so, that we know that much. However, we're told to find the variance of x times y. And this is maybe a little bit tricky. The trickiest step is, I'll show in a second, but basically this solution here does actually do a pretty good job of explaining it, but I'll go through it line by line anyway. So we take the variance, and we have this relationship like that var z is equal to, e z squared minus e z squared, like that. And basically what we're doing is we're plugging in, we're saying that z is equal to x, y, in order to be able to use this formula. So that's how we get this first line. We plug in xy into this formula, and so we end up with e of xy squared, which is, this, and e of xy, and then that whole thing squared, which is that. Like that. Okay, so this is basically using this formula, and you should definitely have this formula on your cheat sheets. This is definitely from like exam 1 at this point, but yeah, all of those formulas that relate the variance and the expected values of things and the variance and the covariance, etc., those are still useful to have, and hopefully you have them from your exam 1 cheat sheet already. Cool. So we have this variance, and we split it up into this, like that. And then the next thing we can do is we can, what is it? If I sort of, I think there's one step here that's maybe useful to show. So e of x squared, y squared, all we're doing is just applying the square to both the x and the y, minus, and then the second one is still pretty much the same. There's not a ton that we can actually do with the second one. And so what happens here is that we have e of x squared times y squared in this expectation. And because x and y are independent, we can actually split up these two into their own unique expectations because they're independent. And so that's what happens. So this e of x squared times y squared becomes this, so e of x squared times e of y squared. And likewise, we can take the inside of this e of xy and turn it into e of x times e of y. So that becomes this, like that. And then, because the two variables have the same sort of distribution, they are independent, but they have the same distribution, we can sort of simplify it by, saying that this is e of x squared times e of x squared, because the second one has the same distribution as the first. And so that's why you end up with e of x squared to the 2 power, because that's just e of x squared times e of x squared. And on the right-hand side, we do a similar thing where we say e of x times e of y is the same thing as just saying e of x squared, and then we square that again, and so that's how we end up with e of x to the 4th here. And at this point, so we're getting very close. E of x, we already know what e of x is, because e of x is just equal to lambda, and lambda is equal to 3 because they told us that, right? So lambda equals 3 because they told us that. And so this e of x we already have, so all we need to do is find e of x squared. And unfortunately, maybe you have it written on your equation sheet, but more likely than not, you don't. And so to get e of x squared, you have to use our favorite friend over here, this one that I'm putting stars on, where you know that the variance of a variable is equal to the e of the variable squared minus the e of the variable and then that thing squared. And we can use that to get this value here. Basically, the way we do that is we can rewrite this. Like if we plug in x here, we know that var of x is equal to e of x squared minus e of x squared, like that. And what we're interested in is we're interested in this thing right here. We're interested in e of x squared, which is this guy here. And so rewriting that, we have e of x squared is equal to variance of x plus e of x squared, because we just moved this over to the other side. And you can see that that's roughly speaking what they do, is they just replace that with the variance of x plus e of x squared. And don't forget that there's this second squared over the outside of this whole expression. So any questions on how we got to this line that I'm underlining right now? Cool. All right. So basically, at this point, all of these values are things that we know. So we know e of x, that's just equal to lambda. We know variance of x, that's equal to lambda. And this e of x is also equal to lambda. So you basically plug in lambda equals 3 for all these values, and then run the math, and you end up with an answer of 63.
Sorry, just one question when you did the last but one step where basically you're rewritten the variance x to add ex whole square to the variance x to get to ex square, right? So we just moved the terms around.
Right, yeah, exactly. Yeah, we went from here to here. This is just literally adding this EX squared to the left-hand side here. That's all it's doing.
Thank you.
Yeah, cool. All right, cool. So that's pretty much that. In terms of similar problems you might see this not being done with Poisson random variables, but with maybe exponential random variables. Or you might see it with normal random variables, or Bernoulli random variables. Or in some weird case, they might not even tell you that it's a well-known distribution, and all they will do is they'll just tell you, oh, it's a distribution, and we happen to know what E of x is, and we happen to know what variance of x is, and they'll tell you what that is, but then you'll have to sort of do all this algebra by yourself in order to use the information that they provided in order to get the desired answer. And yeah, so just know about that. Cool. Question 3. So the runs up and down test is most often used to test for goodness of fit of observations. But of course, this is false because it's a test for independence. One thing I will point out is, let's see, I think I had some notes somewhere. Okay, well, I'll write some notes. One thing I want to just briefly touch on is that the different types of tests. So recall that when you are evaluating a random, or actually, hold on, let me backtrack. Relating to question 3, there's sort of a bunch of tests. So there are goodness of fit tests. Goodness of fit tests. And there's 2 main types that we learned in this course. One is the chi-squared goodness of fit test. And the other one is the Kolmogorov-Smirnov, I'm not pronouncing that right, the KS test. So the chi-squared goodness of fit test and the KS test. And the other thing that we also studied in that same unit was the independence tests. So we have independence tests. And we have, for that, we have the runs up and down. And we also have the runs above, or is it called runs above and below the mean, I think? Above,
yes, you're right. Yeah, it's runs above and below.
Below the mean. Yeah, and I would make sure that you know how to run these tests. So know how to run this one. Definitely know how to run that one, this one as well. In some cases, some of these tests might have tables that you might not have access to, because as you know, the exam has these tables. The exam has like basically 3 tables. It has a standard normal table, and it has a critical value t table, and then it has a chi-squared percentage points table. But for some of the more advanced tests and other things, we don't necessarily have tables. So in that case, we don't have tables provided to us on the exam usually. So in that case, the question will usually be worded in such a way where they will tell you what the value is if it's not something that you can compute yourself. So anyway, but yeah, definitely know how to actually do these different tests on some data that's given to you, because that can definitely come up on the exam. Cool. So yeah, back to this runs up and down test. Yeah, exactly. That's false because runs up and down is testing independence. Drawing an arena decide module. It's a sideways diamond. Honestly, so when I took this class, my memory is terrible. I literally actually on one of my cheat sheets, I drew some arena module shapes just so I wouldn't have to, because my memory is terrible. And also, one thing I did, I don't know, different people have different ways of remembering some of these arena concepts. Like some of the questions are asking things like, in what arena template would you find the sequence spreadsheet? What I did was I made a list of the templates and I wrote in tiny font all of the different, I guess, like modules within each of those templates. And yeah, it took a little bit of time to write it down, but then I sort of didn't really have to worry about questions like question number 5 after that. So yeah, some of these questions suck. Yeah, I probably would just, review the homeworks on Arena, review exam 2, which covered a lot of Arena things. Yeah, it's just more basic Arena questions. In Arena, what module can you use to merge multiple entities into one? Batch. That should be pretty clear. 7, they tell you to describe and show how to implement in Arena the following inventory system. So this test is going to be all multiple choice. So you're not going to have to, like, it's not possible to have a question fully like this where you have to actually draw things out. It's probably a much better use of your time just to be familiar with all of the Arena things that were shown in class. And if you're feeling weak on some of the stuff, just rewatch some of the Arena videos so it becomes kind of like fresh in your mind again on how different scenarios are modeled. Cool. Question number 8. Suppose that we have some uniform random variables and we have a chi-squared goodness of fit test, and they're saying that a 95% chi-squared goodness of fit test will incorrectly reject uniformity of the observations about 5% of the time. And of course that's true. That's just kind of like the definition of this saying 95%. Yeah. Cool. So question 9 is a slightly more interesting one that's mathematical. So we have a bunch of standard normal random variables, z1 through z6, so that's 6 of them. And they were obtained by some method. In this case, they tell us that they were obtained by the Box-Mueller method, but they could have been obtained in any way possible. It doesn't really matter how they were obtained. So, this doesn't really matter for the purposes of this question. However, the question is saying that if you take the sum of these, sorry. The question is saying if you take the sum of these of the squares of these 6 standard normal random variables, that it claims that you will get an Erlang with parameter 3 and 1/2. And of course this is true. And there's a couple different relationships that I just kind of want to highlight here. One, of course, is that if you have, let's say, Z1 and Z2 are normal random variables with a mean of 0 and a standard and a variance of 1. And notice that when it says standard normal means the standard part here means that the mean is 0 and the variance is equal to 1. That's the definition of the word standard in this context. So that's good to know. So anyway, back to this. If you have 2 standard random normal variables, then one of the relationships is that z1 squared plus z2 squared is distributed as an exponential random variable with lambda equal to 1/2. So that's one relationship. And the other relationship is that, Z1 squared is distributed as a chi-squared variable with parameter 1. And if you take Z1 squared plus Z2 squared, that's distributed as a chi-squared parameter, chi-squared variable with parameter 2, and so on and so forth. So if you added up 4 of these, then you would have chi-squared with a parameter of 4. And in particular, they do mention in the solution that the sum, if you have 6 of these guys, that it's chi-squared with 6. There's sort of 2 ways that you can get to Erlang of 1/2. One way is to know that there is this additional relationship where basically, let me think. There's this additional relationship that if you have a chi-squared variable with, let's say, 2n, where n is some integer, then that's distributed the same as a Erlang with, Erlang with parameter 1/2, and then on the bottom is just n, like that. And so that roughly can apply here. So here we have chi-squared of 6. So if 6 is equal to 2n, then n is equal to 3. And so you have Erlang of 3, and the parameter is equal to 1/2. So this is option 1 to get to the answer, is to just kind of know this, maybe have this on your cheat sheet. Option 2 to get to this answer is, we know that Z1 squared plus Z2 squared is exponential with lambda equals 1/2. However, in our case, we actually have Z1 squared plus Z2 squared plus Z3 squared plus Z4 squared plus Z5 squared plus Z6 squared, which is equivalent to saying we're adding up 3 variables that are exponential with a parameter of 1/2, with lambda equals 1/2. And of course, we know that exponential 1/2 plus, let's say, exponential 1/2. If you add up exponential random variables, we know that that's how you get an Erlang variable. So that's exponential 1/2. That's the same thing as a Erlang. Sorry, my browser's not working the best. 3 1/2. If you only had 2 exponential random variables here, then this would be an Erlang of 2 down here. But the lambda parameter would still equal to 1/2. So, yeah.
So if it is like z cube I, then in that case, what it would be? The Erlang, would it be 1/3? Erlang 3 1/3, or
If
the same question?
Z cubed instead of Z squared?
That's correct.
I don't know if there's an easy way to know what Z cubed would be. I'm not very familiar with that.
Okay.
Yeah.
So this is not a generalized thing. It's like only the thing which we can get is like Z square out there, the summation of Zi square, right?
Yeah, correct. Yeah.
Okay.
And what is it if Z is not an even number, as in it's not Z1 to Z6, it's Z1 to Z5, let's say. Then what is the way to calculate?
I'm sorry, can you speak up? It's a little hard to hear you, and I also didn't understand the question.
Basically, right now we are adding Z1 to Z6, right? And we got Erlang 3 because we were able to make pair. What if it is It is Z1 to Z5.
So instead of 6, you have 5, so it's not a multiple of 2. I think that's what he's asking, because you got
Yeah,
Erlang 3 because you added 6.
Yeah, so in the case that you only have 5, then it's not going to be a nice Erlang variable in that case. Because Erlang, this whole exponential requires pairs of standard random normal variables. If you have fewer than a pair for the last thing that you're adding, then you're adding something else weird, and it's not going to easily decompose into a nice variable like this. Yeah, I don't think you'd see that case on a test, unless it's like a true false, where you just kind of have to see that, I guess, that they were off by 1 and that they're trying to test that. But I don't know. I doubt that you'd see that would be really tested. At least based on my experience in this class, they're much more likely to test these nice simplifications where you, for example, have 6 standard normal random variables and they simplify to an Erlang variable.
Okay, so Erlang plus normal is not a defined Erlang plus a normal distribution is not a defined distribution. It's not a properly defined distribution.
Wait, you're saying that Erlang, you're asking if the Erlang distribution is not properly defined? Is that what you're saying?
No, I'm saying that Erlang plus a standard normal distribution is not properly defined.
Yeah, I don't think there's a fancy name for that. Yeah. Yep. Cool. Question 10. So in this question, we have 100 random variables, x1 through x100, and we are told that these are discrete random variables where the probability of x equals 0 is equal to 1/2, and the probability of x equals 2 is equal to 1/2. And they're saying that we want to define the sample mean as x bar equals to, as you would expect, just add up all 100 random variables and divide by 100. And then they want us to use the central limit theorem to find an approximate expression for the probability of the sample mean being less than 1.1. So, yeah, I think they do a sort of reasonable job here, but we can kind of go through it step by step. It might be useful to go through it step by step. So let me go to my other piece of paper here. Yeah. Are people okay with me going through it sort of step by step, or would people just prefer me to just talk about what's here and then move on?
Yes, please. You can go step by step. For me, it's like if everybody agrees. So
absolutely, yeah, we would definitely want to see more. Thank you.
Okay. All right, cool. I'll go step by step. So recall that we have x1, x100, and these are each distributed according to this rule where the probability of how should I say, x equals x is equal to 1/2 if x is equal to 0 and 1/2 if x equals to 2. See, did I write that down correctly? Yeah, okay. Cool. And we are also told, of course, that we want to find what the probability of the sample mean being less than 1.1. So this is what we want to find. Cool. So how do we get this? And this is, like if you see this question on a test, it honestly, like, it might be a little bit overwhelming because you're like, I'm very confused. But thankfully, the question does say to use the central limit theorem to find an approximate expression. So because that's basically a very key hint in this one. they're saying to use the central limit theorem, which this should be on your equation sheet, I think, as well. And let me find the actual expression. Using the central limit theorem, we know that let's say, basically, we know that in this case, since we have these 100 variables, we know that the sample mean as an approximation is distributed as a normal random variable with mean mu and sigma squared over n. And so mean mu, this is just ex, and sigma squared is just var x. And to be pedantic, I'll say xi, because all of these x's are basically distributed the same, and they're independent. So e of xi, and the sigma squared is equal to var of xi. And
can I ask a question? Sorry, quick question here. When we say normal mu comma sigma square by n, or sigma square, because in some places we take mu comma sigma square as a variance, and some places we take sigma square by n as a variance. And when there is sample involved, we are taking by n minus 1. So could you quickly elaborate? Is it when we say central limit theorem, we are supposed to take sigma square by n?
So this is really, let me sort of step back and talk briefly about something real quick on this. So this is sort of like a notational issue. So suppose you have a x is a random variable, and x is a random variable, and if we say that x is distributed as normal, and there's some number here, comma, some number here, whatever is here is the parameter of the normal distribution representing the mean of the normal. So this is like the parameter mu, and whatever is here, shut up this, okay. So whatever is here is the parameter sigma squared of this normal distribution. So like whatever is here, whether it's 5, whether it's 10, this is the variance of this normal. So we're basically saying that x is distributed according to a normal distribution, and that normal distribution has, by definition, some mean mu and some variance sigma squared. So that's the basic thing. But it's a fair point. You can see here we're saying normal mu and sigma squared over n. But basically what we're saying, this is sort of an abusive notation, because this sigma squared here that we show here is not the variance of the normal. This whole expression here is the variance of the normal, this whole expression. And likewise, this whole expression is the mean of the normal. Basically the same as over here. Basically everything that's here is the variance of the normal, and everything that's here is the mean of the normal. So the question is, what does the sigma squared represent? This sigma squared that we write here is not the sigma squared of the normal, but the sigma squared of one of these xi's. So, basically this sigma squared actually is the variance of the xi. So I'm going to make a link to that, because this is the same thing. So, and this n, in this case, represents the number of variables, which is n equals 100. So we have n equals 100. Does that maybe help a little bit?
Yes.
Okay, great.
Well, when do we use n minus 1 instead of n?
So you use n-1 when you are computing the sample variance of actual observed data. In this case, that doesn't apply here. I will talk about that, but yeah, the sample variance is something very different from the central limit theorem. So this equation here that I'm gonna circle in green, this is according to the central limit theorem, and it's different than the n-1 thing you're talking about.
Thank you.
Mm-hmm. Yeah. Cool. So basically what we need to do is, so we know that according to the central limit theorem, we can approximate the distribution of x bar, which is the sample mean, by this normal distribution. And then we know how to find the probability that some normal random variable is greater or less than some number. And all that involves doing is just transforming the inequality into a z-score sort of thing, and then looking it up in a table. But in order to do that, we do have to figure out what this mu is here, what this sigma squared is, and what this n is. So we know that n is equal to 100. We have n equals to 100, so we have that. This mu is equal to e of xi. So what is e of xi? Well, we actually have to calculate that because they didn't tell us that. They told us what the probability mass function is. They told us that x is equal to 0 half the time and x equals 2 half the time. But in order to calculate actual e of x, we have to basically, multiply the probability that x is equal to 0 with, times, so you multiply x times the probability of x, which is 0 times 1/2, plus the other one, which is 2 times 1/2. And so that's equal to 1. So e of x is equal to 1. So that means we have this, we have this mu, that's equal to 1. And the other thing we need to do is we need to calculate the variance of x, which is just, so that's sigma squared. Sigma squared is equal to the variance of x in this case. And recall that there's kind of a couple different formulas you can do. Probably the most basic formula is the one where you take, hold on, let me think how to explain this. The summation,
so ex square that we saw earlier, like ex square minus ex whole square.
I see. So you're saying, I know what you're saying. You're saying, let me find that one. Thought I had it somewhere. Maybe I probably wrote it somewhere else. Anyway, you're saying, scroll up just so everyone knows what you're talking about. Okay. Aha, you're talking about this one right here, where you have the variance is equal to, some thing squared and then there's some other thing squared. So you can do it like this, for sure. And if you wanted to do that here, you would simply have to calculate what e of x squared is. Alternatively, you can use the definition, which is like if it's basically by the, like if it depends on whether it's a continuous or a like if x is continuous, then it's, I believe, integrating from x minus e of x squared, like that, if I'm not mistaken. So this is if for continuous random variables, and for discrete random variables, there's a summation that's very similar. Actually, I forgot one thing. So it's x minus e of x squared. And I think there's also like an f of x in here. I'm pretty sure. I think. Probably. Anyway, but yeah, for var of x, we take like the probability that you see that x equaling the x value, and you multiply it by the x value minus the, I guess, the e of x, and you square that. So if I sort of, I would double check this continuous formula just to make sure I didn't make a mistake. I don't actually, I'm having trouble finding it on my equation sheet, so I don't want to mislead you. So double check that. But in any case, for this discrete value case, what we have is we have 1/2 times the first one, which is 0 minus 1 squared, plus 1/2 times 2 minus 1 squared. And this 1 comes from the e of x. This 1/2 comes from the probability that x is equal to 0, and this 1/2 comes from the probability that x is equal to 2. And when you do this math, this becomes 1, this becomes 1, so you're adding up 1/2 times 1 plus 1/2 times 1, so that equals to 1. So now we know that the variance of x is equal to 1 in this case. And therefore, we also have this thing as well. So now we can actually say that our x bar, which is our sample mean, that's distributed as a normal random variable with mean of 1 and variance of 1 over, I guess n is equal to 100, so 1 over 100, like that. So we know this, and now sort of the final step is to use this information to find the probability that x is less than 1.1. So what we can do is we have this probability x bar less than 1.1, and we can sort of, using the z-score approach, we can add things to the inside of this inequality. So we can take x bar, and here's our less than sign, and we have our 1.1. We can subtract the mean from both. So we can subtract 1, because that's the mean. So this is mean mu. And we can subtract it here as well. And of course, if you subtract two numbers from both sides of an inequality, the inequality doesn't change. So this is still valid to do. And we can also divide by sigma, I believe, if I'm not mistaken. Actually, no, it's not sigma. Yeah, it is. It's divided by sigma, right? And so divide this by sigma as well. And sigma is equal to, the square root of sigma squared, which in this case, for this sigma squared that we have here, that means that sigma is equal to 1/10. So
sigma square here is why it is not 1. I thought that it is 1 because sigma square by n, right? We said so. Sigma square. That's how I see. It's like I was just wondering that when you converted into like norm, 1 by sigma square by n. So So this sigma is different from,
Yeah, so this, like I said, I'm sort of abusing notation here because
Okay.
if we're really being pedantic, then this sigma would be like sigma x.
Okay, so these are two different sigma,
Yeah,
not the
and
same. Okay.
yeah, this
Okay.
sigma is really like sigma of this normal random variable, which we'll call like x bar or something like that. I don't know. Yeah, so
Okay.
this
Thank
is,
you. It's like I just wanted to see.
yeah.
Thank you.
So yeah, and so we know that that if you take a random variable that is a normal random variable and you subtract the mean and you divide it by the variance, by the, I guess, square root of the variance, then we know that that is equal to a standard normal. So that's just a normal 0, 1 random variable. And doing the same thing over here on the left-hand side, 1.1 minus 1 is 0.1, and then dividing it by 1/10 gives you 1, like that. And so we've basically simplified from this to this much simpler version where we just need to find the probability that a normal random variable is less than 1. Does it make sense how we got from that to that?
So we always try to use this on the one step above the last question you derive, that probability of x bar minus 1 divided by sigma. So this is the standard thing to put it into norm 0, 1, right?
Right. Yeah, so
Okay.
this mu is equal to, let me use the colored thing. This mu is basically coming from here, and this is equal to, this is basically sigma squared, and so then you take the square root of that to get 1/10, and then you plug it in here.
Okay.
Yeah.
Thank you.
Anyway, so we end up with that, and at this point, once you see the probability that the normal 0, 1 is less than 1, we can go to our table, and the top table, you basically, the probability that a standard normal is less than 1 is 0.8413. So that is just equal to 0.8413 from the table. And oops, let me go back to the exam. Scrolling down. And here we are. So here we have 0.8413. Yeah. So yeah, they kind of did a lot of steps here at once, but yeah, they did the exact same thing I did. So cool. All right, so moving on. Actually, one thing I will talk about briefly, just for variance, there can be a large possible number of variants to this question. You could have these x's be, lots of different things, or they could tell you what the variance or the e of x is, or something else could happen where you have to transform random variables into a normal random variable, and at the end you have to, do the same sort of thing to look it up in a table. But yeah, I would definitely look at maybe some of like exam 1's practice questions for similar things to this, because I think that those things could come up in various forms, and it's good to have that down pretty strongly. Cool. Question 11. If you have two random variables that are uniform on the interval 0 to 1, what is the distribution of this minus this? The first thing, hopefully you guys are starting to see a pattern that whenever you see a natural log of some uniform random variable, that it's probably an exponential random variable. Because, of course, you know the old rule that, let's see, if you have x being distributed, sorry, if u is distributed as a uniform 0, 1, then x is equal to minus 1 over lambda times natural log of u is distributed as an exponential with parameter lambda. So basically, you can see that there's already a lot of similarities. We already have a minus sign in front of the natural log, just like this. And it is kind of weird that we have the square root, though. But this is where you use your sort of well-known natural log math skills. And you know that natural log of square root of u is equal to natural log of u to the 1/2. That's basically just equivalent and definition-wise. And you know that anytime you have something to an exponent inside of the natural log, you can actually bring the exponent up front. And so it's negative 1 over 2 natural log of u. And at this point, you can basically see that this fits our pattern exactly. So we have lambda equals 2. And so this is an exponential variable with lambda equal to 2. And likewise, this minus natural log of square root of v is the exact same. So overall, this whole thing is basically equal to the sum of two exponential random variables. So we have an exponential 2 plus another exponential 2. And we know that that is equal to an Erlang 2 of 2, like that. So that's really all it is. Yeah, this is mostly just being able to see that, oh yeah, there's a pattern here where there's a natural log of some uniform random, so we're probably going to have to do some minor manipulations to transform it to an exponential, like this, and then we just add them up and get our Erlang at the end. Cool.
Okay,
Can I ask you
I have a question on that.
Oh, sure.
Why can't we say that the square root of u is also u?
Because that doesn't make sense. Like, u can be any number between 0 and 1.
Same.
So, like, let's say that
square root also will be between 0 and 1. So
yeah,
that
but
also is a random number.
So you're saying that square root of u is equal to u. But let's say that u is equal to 0.5, then square root of 0.5 is equal to, what is the square root of 0.5? It's like 0.7183 or something. I don't know. Some number.
Yeah, whatever.
But that's not equal to, so that doesn't equal to 0.5 though, right?
It does not,
So
but in this case, it's just a uniform number, right? So in the sense that we're taking it as a uniform number.
Well,
if I can,
this is a uniform random variable. It can be any number between there, but once you get a realization of this uniform random variable, you can't say that u equals square root of u. That won't work because whatever number you pick is usually not going to equal the square root of itself.
Because, when we were doing this thing in the slides, the professor had written in multiple distributions that, u is equal to 1 minus u.
Okay, so that's a different thing. That's correct. A uniform random variable that's That's different though than square root of u. Basically, okay. Let me try to show that.
How will that be different?
Yeah. So
If
go ahead. Maybe you can.
Yeah,
provide
if I can jump in, the thing is that the square root is not a linear transformation. So yes, your output values are still going to be from 0 to 1, but the probability of having a specific number is not going to be uniform anymore. You're changing the shape of the distribution because your transformation is not linear.
Clear. Yeah, that makes sense. Yeah.
Yeah. Yeah. Well, and let me talk to the point. So let's say that you have a uniform 0 to 1, and this is our u. It's distributed as a uniform 0 to 1. That means that, as you're taking a bunch of realizations from it, you'll have like a bunch all throughout this interval, 0 to 1. They'll all be here. And if you do the same thing and look at 1 minus u, then that means, like, let's say that these guys here, 1 minus this, are going to become these 3 here. And likewise, the ones in the middle, 1 minus about 0.5 is going to end up being about 0.5 here. So these ones are going to go here. And likewise, these ones are going to, 1 minus something close to 0 is going to equal something close to 1. So this is, 0.5, and this is 1. And, you can do the same thing with all of these. And basically, you can kind of see that we still have the same sort of distribution as we did before. It's still a uniform between 0 and 1. And so that's why you can do that sort of trick between u and 1 minus u. However, if you tried to do this with u and square root of u, you would find that this thing doesn't happen.
Yeah, clear.
Yeah, okay, cool. All right, so moving on, question 12. True or false? If we want to generate x as a Poisson variable with 4.5, then it's better to use a normal approximation than acceptance rejection. And this is false. So in the explanation here, it says that the normal approximation requires larger lambda for the asymptotics to work and the efficiency to kick in. Specifically, the specific rule that you want is that if lambda is like above 20, then normal approximation is okay. Normal approximation. Okay. Yeah, and otherwise, lambda less than 20, acceptance, rejection better. Or better. So anyway, in this case, lambda is equal to 4.5, which is a lot less than 20. So acceptance, rejection is better because you really need to have this lambda to be pretty big before you can start to rely on the normal approximation. So that's pretty much that one.
So are there similar values for different types of distributions where normal approximation would be better versus not better? Or is it only for Poisson we have, like you mentioned, lambda is 20?
So this is just a rule of thumb, right? But yeah, for different distributions, there will be different values for sure. I agree with that. Yeah, I think the main one that you're maybe responsible for is the one for Poisson. But yeah, I mean, other distributions have this as well, but you probably won't be tested on those values because I don't think they were mentioned in lecture. But if they were mentioned in lecture, then feel free to write it on your equation sheet. I know that this lambda equals 20 business was mentioned in lecture specifically. So
Thank you.
yeah. So question 13. The acceptance rejections majorizing function t of x is usually a PDF. So this is false. This is just the definition of what the majorizing function is. Yeah, there's not much else to say on that one. Next one, question 14. This is actually, I believe, testing content that is optional. So we're not going to go through that. I believe it's optional. Question 15. If x1 through xn are IID exponential of 1/9, what is the expected value of the sample variance s squared? Okay, cool. So this is another kind of big thing that you'll most likely see this on the test in one way, shape, or form. And it's the idea that, so s squared is the sample variance, and it is unbiased for true variance. And the true variance is sigma squared. And then there is also the maximum likelihood estimate for sigma squared, which is sigma squared hat. So this is the maximum likelihood estimate for the variance. And this is biased for true variance, sigma squared. And so what this means is that if you take, if you were to take a bunch of samples an infinite number of times, E of s squared, if you take all these samples and you calculate a sample variance a bajillion times, and then finally you take the expected value of that, which is, just the average, I guess, then you should get the true variance. However, if you do the same thing with our maximum likelihood estimate of the variance, this will not equal the true variance. Because this one is biased. So, and this goes back to something someone said earlier about the 1 over n minus 1. So this is where that comes into play. Find my notes just to make sure I'm saying all these things right.
So here sigma square is the true variance and sigma hat square is the estimated variance, right? You're saying, or maximum likely.
So the true variance is sigma squared here. This is the true variance.
And s squared is the sample variance, correct?
S squared is the sample variance, yep.
Yeah, this terminology is a little confusing because this is, we use sigma square, s squared, that's clear, population versus sample. But the sigma hat square is the estimated value of the population variance, correct?
It's the maximum likelihood estimate for the true variance. Yeah, I know it's definitely a mouthful. And you'll probably see this in some way, shape, or form. I mean, you can already see that this example, well, in this case, they ask, what is the expected value of the sample variance, s squared? Well, we know that because the sample variance is unbiased, that the expected value is equal to the true variance. And so because we know that for an exponential variable with lambda equals to 1/9, we, from your cheat sheet, should know that the variance is equal to 1 over lambda squared. That means that if lambda is equal to 1/9, that the variance is equal to 1 over 1/9 squared, which is equal to 81. And that's how you get your answer. Because, but this question can show up in a lot of different ways. They can ask you like this to calculate a number using that fact, or they can just say it as a true or false statement. They can say as a true/false that sample variance is unbiased for the true variance, for example, And yeah, so that's, or another thing they might ask you is, what is the expected value of the maximum likelihood estimate for the variance? And in that case, you would have to calculate, basically, there's a relationship between the expected value of this one and this one. And it's a factor of n minus 1. But let me show you let me just write it down here, how you actually go about calculating these things. So to calculate s squared, it's equal to 1 over n minus 1 times the sum. I'm just having a brain fart here. It's
xi minus x bar whole square, I think.
Yeah,
right?
That's right. Yeah, xi minus x bar squared, that's right. Like that. Yeah, where x bar is the sample mean. Yeah. So, yeah, this is the formula for s squared. And the formula for our maximum likelihood estimator is 1 over n times the same thing, xi minus x bar squared. So the only difference is that in this case it's 1 over n minus 1, and the other cases it's 1 over n. And that turns out to make the difference. Yeah. And recall that, yeah, this formula, the maximum likelihood estimate formula, looks very similar to the true variance formula. But yeah. Anyway, so just remember that this one is biased and this one is unbiased. Yeah, you will most likely end up having to calculate s squared sometime on the test in one way, shape, or form. Cool. Question 16. So if you have 3 normal random variables with x1 equals 3, x2 equals 2, and x3 equals 7, what is the maximum likelihood estimate for e of xi squared? So what you can do is you know that for normal random variables, we know that what is it, the maximum likelihood estimate for the mean, that's just equal to the sample mean. And we know that the maximum, and actually that's so e of x, I guess like that, that's that thing. And we also know that the maximum likelihood estimate for the variance of x, which is equal to, sigma squared hat is equal to 1 over n times the sum from xi minus x bar squared. However, in this case, we want to find the maximum likelihood estimator for xi squared, which is neither one of these things. But what you can do is, you know that from our trusty formula that we saw earlier, the one where you have var x is equal to e x squared minus e of x squared. We know from this formula that if we want to get this number, we just add up the variance and this number. And so that's basically what we're doing here. this E of x is just we make all of these maximum likelihood estimators by adding hats to them. And this E of x squared is just this guy right here, which is the mean, the maximum likelihood estimator for the mean squared. And the maximum likelihood estimator for the variance is this guy right here. And finally, the value that we're interested in calculating is this guy right here. And so at that point, this value we already know is just x bar, and then you obviously have to square it, so that's easy. This guy's easy. And this sigma hat squared is just using this formula over here. And they actually write this formula in a kind of interesting way. They write n minus 1 over n times s squared. This is exactly the same thing as this. Like you can convince yourself of it because, since s squared is equal to 1 over n minus 1 times a bunch of stuff, which is the same.
It's something that you wrote right above.
What was that?
Something that you wrote right above, like in the previous problem that we had.
Yeah, something like that. Yeah, they're very. Yeah, so this is equivalent to this. I won't waste people's time by talking more about that. But yeah, you just basically plug in the numbers and you get your answer. Yeah. Cool. Question 17, find x such that e to the 2x equals 1 over x. This is definitely from one of the earliest, like the first third of the course. I'm not going to spend too much time on it. I will comment that there are two ways to do it. Either you can actually use bisection. Actually, there's more than two ways. You can do bisection actually and find it that way. Another way you can do it is if you have a graphing calculator, you can graph both of these, see where they intersect. A third way is you can actually sort of maybe do the math, maybe do some calculus to see what the value is. Regardless of which way you get the answer, you can get your answer somehow. I won't talk more about that. Cool. Question 18. This is true or false. The square root of the sample variance is unbiased for the standard deviation. And so this, of course, is false because although the expected value of the sample variance does equal the true variance, that's what I discussed earlier, the expected value of, if you take the square root of this, this is not true. So this is not true like that. Yeah. And that's kind of, I mean, mathematically you can prove it to yourself, but this is just a really common good to know fact. And it's a pretty common test question, as you can see here. So that's good to know. Question 20. Suppose we're conducting a chi-square goodness of fit test to determine whether or not 200 IID observations are from a Johnson distribution, which has 4 parameters that must be estimated. If we divide the observations into 10 equal probability intervals, how many degrees of freedom will our test have? And yeah, this is really simple. It's equal to the number of buckets or intervals minus the number of free parameters that we have to estimate, and then you subtract an additional 1, and you get your answer. So that should be a really easy one. Question 20 is a bit of a longer one. Also, I know that we've been here for 2 hours, but I'll just keep going. I want to get through this test today, so I'll just keep going, even though we are over time. You guys are welcome to leave or go, or, this is being recorded, but yeah, I'm going to just keep going so that way we get through this test today. So, question 20. We are interested in seeing if the number of emergency department visits occurring each day at the Georgia Tech Clinic is binomial. So we have some visits and we have some number of days that contain that number of visits. So how many intervals will you use for your test? A lot of this stuff is it's just pretty similar to the stuff you did on your homework. It's, it's probably, how should I put it? Yeah, basically the number of intervals can, like, roughly speaking, just be, or how should I put it? So the way that we get our intervals is by looking at our expected distribution, which our expected distribution is binomial. And then what you do is you sort of try out different values for your distribution and get your buckets from that. So like if we had a uniform distribution that we were trying to test against, then all of our buckets would be, like uniform values, a little bit different. And that's why like our E of I is different for different buckets. Yeah.
What is the interpretation of what we're testing? Like, are we looking to see if the probability of 5 visits in a day is 0.5?
We're trying to see if the distribution of the number of visits per day is binomial. So that's our hypothesis. We're trying to test whether or not that is the case. And to that end, we are using the chi-squared goodness of fit test, because the goodness of fit test is, there's multiple goodness of fit tests. There's also the KS test. But the goodness of fit tests are what you use to compare the data that you see to an expected distribution, and to be able to say with some degree of statistical certainty that, oh yeah, the data that I'm seeing does match up to this distribution that I think it is. Does that make sense?
Okay. Yeah, I guess I was just like I was surprised by the outcome because I thought it was saying that that's a pretty probable outcome, and there was only 7 days that had 5 visits.
I'm not following your question. When you say outcome, you mean the conclusion in part C?
Yeah, and B too.
Oh, so basically, yeah, so we're failing to reject. So yeah, we're assuming that it's binomial, the conclusion. And if you look at that, that sort of makes sense because the observed numbers here, 6, is very close to the expected number, 6.25. Same thing with 30 and this one, 61 and this. These numbers are all very close to the expected number when you do the bucketing. So it makes sense that we would fail to reject and thus get a conclusion that it is binomial.
Okay, yeah, I see that. I think I just got stuck on the binomial 5.5 thing, and it might just be my understanding of the binomial distribution is not quite right.
Yeah, well, so yeah, binomial has 2 parameters, right? It has both, I guess, binomial has both n and e, I believe, right? So that's why there's this 5 and this 0.5.
I think the number of trials and the probability, right?
Yeah, exactly. Mm-hmm.
So would that be like every 5 visits, the probability of or every 5 days, the probability of a visit is 0.5?
No, it's saying in a single day, how many visits are you going to see in that day?
Okay.
Mm-hmm.
Sorry,
So,
I did.
so
This is kind of
the
a
example.
sidetrack.
Yeah. All right, cool. Moving on. So, if you write out this table, you can use it with this formula to calculate the statistic value. And you can compare that statistic value with the critical value. And because this statistic value is a lot less than the, because this statistical value is a lot less than the critical value of 11.07, we fail to reject, which means, so when we say fail to reject, just to clarify, we initially, in the goodness of fit test, we have a hypothesis that the data is from this binomial distribution. So if we fail to reject that hypothesis, then that means, so that means we'll assume that it is in fact from that binomial distribution because we didn't find evidence otherwise. The way we would find evidence otherwise is if our statistic value was bigger than our critical value. Cool. Question 21. Here, this is an example of using the K.
Sorry, one quick question on the alpha value here. Some places we are using alpha by 2, in some places we are using alpha. Here it is just alpha, right?
Yeah.
Or did we? Yeah. Okay.
Yep. Yeah, that's right. So question 21, we have the KS goodness of fit test to see if the numbers are uniform 0, 1. And you can see they basically do everything for you. They do this whole table thing to get our DN value. And in fact, this question is only asking us what is the value of the test statistic. So it's not even asking us, is this, do we reject the hypothesis in this case? It's not even asking us that. It's just asking us to find the value of the test statistic. And in particular, I believe that to actually find the critical value for this test, you would typically have to have a table given to you, or they would just tell you what the critical value is if they needed you to actually use that somehow. So that's pretty straightforward. It's similar to, I think, some questions on the homework and or in the lectures. Question 22, do the pseudo-random numbers in question 21 pass the KS goodness of fit test for uniformity at level alpha? So this is what I was talking about. They mentioned in the solution that from the one-sided table, they have the critical value here equals 0.565. However, obviously, if you're not in a test setting, you can look it up in the one-sided table. But in a test setting, you might not be given it, and so the test would probably just tell you that, this is equal to this, or it would give you like a really tiny condensed table that you would have to read, and then you'd have to use that information to decide whether to reject or fail to reject. Yeah. Cool. Question 23. This is another stochastic process question, which I believe is out of scope per the syllabus. Question 24. Consider the following approximately normal average waiting times from 4 independent replications of a complicated queuing network. So suppose that each output is based on the average of 500 waiting times. So each one of these is basically already an average, where you took 500 different times and you averaged it together, and at the end you got 30. And same thing with this 40, this is another 500. So here they want us to use the method of independent replications to calculate a two-sided 90% confidence interval for the mean mu. So this is pretty straightforward. This is just, for the most part, applying some equations. So I would recommend on your cheat sheets to just have these equations written out. The ones for method of independent replications, the equations that you used for batch means, the equations that you used for difference of means, or for confidence intervals of difference of means, as well as, for example, like you can have like paired like finding the confidence interval using the paired method, which can actually reduce the variance and reduce the size of the confidence interval. There's a bunch of those things, and I would recommend just having all those equations on your equation sheet and knowing how to use them. So in this case, we're using the method of independent replications to calculate this two-sided 90% confidence interval. Notice, so yeah, you can follow this math. This is very similar to stuff done in lecture and stuff on your homework. But at the end, you get a confidence interval. Question 25. Which is the method of batch means more appropriate for, terminating or steady state simulations? And this is just obviously a steady state. That's sort of one of the requirements. And that makes sense, right? Because in a batch mean method, what you're doing is you have some simulation that, is producing some data over time. And then what you do is you split it up into batches. So, you have like this be a batch, this be a batch, this be a batch, this be a batch. And of course, if you are doing a terminating simulation, it's more likely that you end up with data that's sort of in this kind of not fully stable period. Whereas steady state simulations, you can skip this like initial period and get to the part where it is sort of steady state and then use that for your batch means. 26, which is usually a better way to deal with initialization bias in steady state simulation analysis? 1, make an extremely long run to overwhelm the bias, or 2, perform truncation. And yeah, truncation is definitely better. Basically what they're saying is, do a really long run where you might like just go on a really long time, and because you went a really long time, then even though this value does contribute some wackiness, because there's only a small amount of it, that it won't matter as much. And so that's what they mean by having an extremely long run to overwhelm the bias. And the second option is to do truncation. And truncation means, use this and, maybe don't do it as long. So like maybe do it only this long, but then truncate where we're only using this part. So that way we don't use this part to the left at all. So, and you can imagine that that's cleaner to do it that way. Cool. Question 27. Use the method of batch means to calculate a two-sided 90% confidence interval for the mean mu. In particular, use 2 batches of size 5. So of course, our batches are these 5 numbers, and then the second batch is these 5 numbers. And so you calculate the batch means, and you plug in the batch means into, the appropriate equations. And after plugging in these numbers, you get a confidence interval. The key here is knowing which equations to use when, because this is using the batch means equations, whereas earlier we were doing the method of independent replications. And the equations are generally similar, but there are sometimes small differences, so it's good to know that and know which ones to use when. Cool. Next question. Suppose you have a 90% confidence interval for the mean mu, and now they've decided that they want a 99% confidence interval for 2 mu based on those same 10 replications of size 1000. And this is sort of kind of an algebra problem, really. And it's just a matter of, knowing that this is the, basically this is sort of the confidence interval for the 90%, and then doing some algebra to be able to get the new confidence interval. I would say a question like that is fairly likely on the exam. So probably good to definitely review that. Question 29. Suppose I use the method of overlapping batch means with sample size n equals 10,000 and batch size m equals 500. Approximately how many degrees of freedom will the resulting variance estimator have? And, these are just equations that you probably want written on your cheat sheet next to the batch means content, where, you know that you can take b equals n divided by m, which is this, 10,000 divided by the 500. And then there's this approximate degrees of freedom calculation where you take that b number and plug it in here, and that's how you get your answer. So the next two questions are talking about Brownian motion, and you'll most likely see something related to Brownian motion on your exam as well. I would strongly recommend that your cheat sheet have a list of the common properties of Brownian motion. Common properties like, I'll just give a few examples. I won't take a long time, but, like one of the slides just had a bunch of properties. It had like W of 0 is equal to 0. It had things like covariance of W of S, comma, W of T is equal to the minimum of S, comma, T. And there's a whole bunch of other properties. It's quite possible that one of the test questions will be something like, which one of these properties is not a property of Brownian motion? And, in that case, it'll be very helpful. Or you might just get a simple, simple test of one of these properties where they'll tell you, you have some W of 10 and W of 5, and they'll say, what is the covariance between them? And, if you have these properties written down, it'll be a really easy answer that will take you no time at all. So definitely write down all the properties. In the particular question 30 here, they want to find that the probability that W of A is less than W of B. And because A is less than B, I believe one of the properties says that in that case, basically, actually, I think in general, just having W of A minus W of B is, normally distributed with mean of 0. And, that means that you have some like distribution like this, but the mean is at 0. And so the probability that one side is less than the other side is just 1/2. And question 31. So suppose that you have this area under a Brownian bridge process. Find the probability that this area is greater than this value. So one of the things you should have on your equation sheet is that if you have this, then that is distributed as a normal random variable where the mean is equal to 0 and the variance is equal to 1/12. And at that point, this question basically reduces to a simpler question, which is, what is the probability that a normal random variable with mean 0 and variance 1/12 is greater than 1 over square root of 12? And that's where you can do that whole z-score thing to transform, to transform this probability, where you have A is greater than this, into a probability that uses the standard normal random variable. And once you do that, then you look it up in the table and you get your answer. And notice that in this case we have a greater than 1, so that's why we find the value for 1 in the table, which is like 0.8517 or whatever, or 1 I forget. And then we subtract, we take 1 minus that to get this answer, because it's greater than here. Cool. Question 32. This is a independent replications question where they want you to find a two-sided 95% confidence interval for the difference in means of the two systems. And as I mentioned before, there's just a lot of equations that you sort of have to write on your sheet and know how to use. And a very similar question is question 33, where it's almost the same, except we now use common random numbers to induce positive correlation. And so the equations and the method is different. So in this case, you find the differences between each of the individual pairs. And then using those differences, you use some slightly different equations to get a slightly different confidence interval. And yeah, this last question is, I think, pretty similar to some stuff on exam 1. However, parts C and D uses the method of antithetics to estimate I. And all that really is doing is basically you use this technique, the first method, with these pseudo-random numbers, and then you do the same thing, but instead of using these ones that are provided, you use 1 minus those numbers, and you get a slightly different answer, and then you just average this answer and this answer to get that answer. And also, so question 35 is talking about ranking and selection, and this is a multinomial problem because you're trying to find the most popular show. Anytime you're trying to find most popular of something, then that's usually where people can only choose one out of multiple, then that's a multinomial problem. Yeah, and they do mention there can be some couple easy ranking and selection questions from Module 10. I would definitely recommend reviewing the ranking and selection questions. Usually the questions will have some sort of format where they'll be like, they'll tell you that you've done the math and you've calculated that you need to have at least 300 samples, and here's the data. You have some, maybe Coke has a approval rating of like 60%, and Diet Pepsi has an approval rating of 50%, and then they'll be like, which beverage, has the highest approval rating? And basically, because you have done the required number of samples already, you just pick the one that has the highest approval rating, for example. Another format they might ask those questions in is in terms of early termination. For example, if you need to get up to 300 samples, but you've only taken 200, well, if one of the winners is already so clearly winning above the other ones that even if you took those last 100, that it would still be winning, even if those last 100 samples went to the competitor, then, you can sort of early terminate. And the question might ask you something about that, be like, what should we do? Should we collect those last 100 samples, or can we just, terminate early? So that's another question, another format these ranking and selection questions might show up in. But yeah, I probably recommend just reviewing the slides on that as well. Cool. I know we went through this second half a little bit faster, but I will point out that these questions here are more recent in terms of the content that you've been studying. The homeworks that you guys have been doing very recently, these past couple of weeks, are more likely to have covered a lot of these concepts, so they should be more fresh in your mind. With that said, what questions do you guys have for me? I'm not hearing any questions.
No, I think you've clarified very many concepts, so that's great. Thank you so much.